Okay, well, it's my great pleasure to be here, and thank you all for coming. And I thank Professor Vipin for organizing everything. Great. Okay, so I thank Professor Vipin for the introduction, and I thank the Dean for the nice, very energetic support for what we're going to do here over the next couple of days. And also nice to finally meet Parth, and we'll have more conversations. My job here today, I think in the first little bit, is just to motivate the kinds of things that will happen over the next couple days. And what I'm not going to do at the moment is to give pedagogical advice about how to create agent-based models. That's coming. That's going to be part of the rest of the couple days. My job really is to simply say, why is this a thing that can be useful both in academia, as was already discussed a little bit, in policy, but also in business. And there are a wide variety of applications that have been made of this technology. And I actually will tomorrow discuss further, more concrete applications. Right now, it's just going to be kind of a high-level discussion, and I want to leave time for questions at the end. So I'll just march right in here and get going. So just maybe some terminology. I say agents, agent modeling, agent computing, agent-based modeling. These are all synonyms for a series of techniques. Not sure why I've lost that. Maybe come back. So yeah, so a series of techniques that really, when I was a graduate student many, many years ago in the late 80s, early 90s, were not even around. But there arose, basically, in the wake of the microcomputer revolution, a lot of work at the intersection of AI of the time, distributed AI, so-called. Artificial life was another term that arose. And so in the early part of my career, I started building a model that I'll show in a moment that we call initially artificial social life. And then subsequently, I've been teaching these kinds of modeling approaches at a number of American universities, first at the undergraduate level and then at the graduate level. And so for 20 years, I've been doing this kind of stuff. And so I'm very happy to say that I'm going to give you guys the benefit of the stuff that I've been doing, and I'm at the moment writing a textbook on this whole modeling approach, trying to address both the nature of the technology, but also details about how to program it, et cetera, that you'll be hearing more about over the next couple of days. So I'm just going to provide at this point kind of a summary, a high-level summary of the kinds of motivations for when we want to use agent-based models. And by the way, as a footnote, I'm happy to provide these slides to everybody if by email or whatever. Okay, first of all, what is an agent-based model? And how is it different from other things like mathematical models, or maybe you've heard of system dynamics models, or some of your economists, game theoretic models. So the main thing we're going to be seeing across all agent-based models for the next couple of days is there's always going to be a population of agents. And those agents are going to be little pieces of software that are going to engage in some activity that we recognize as being relevant to the process we're trying to deal with, trying to model. So you care about inventory management. The little software is going to be doing something associated with increasing or decreasing the inventories. You care about modeling markets. The little piece of software, the agent will be doing something about buying or selling in a financial market. So we're not really going to be programming our computational models to solve equations. We're going to be basically building up a population of these little software agents, and they're going to be doing things. And I'll give a concrete example in the next slide, but for now, suffice it to say that these agents are going to all have their own ideas about how the world works. They're going to have their own rules of behavior, either fixed or evolving, possibly a meta rule, like something just make myself better off. They're also going to have internal data about the world they're in. And importantly, that data is going to be heterogeneous across the population. So the agents are going to be different. So immediately one contrast with conventional mathematical modeling is that in mathematical modeling, it's oftentimes hard to have heterogeneous things. We're going to, for example, in economics, macroeconomics, we'll have a representative agent, a typical agent. But in agent-based modeling, we'll try not to have that. We'll try to have heterogeneity, and I'll show you some examples here in a minute. What I've just said about heterogeneity. There's also oftentimes some environment. Now, the environment could be a physical, natural environment, like agents running around on a landscape, or the environment could just be other agents, and other agents in some kind of social environment. And so we'll have some representation of this, whether it be an explicit, say, graph or network, or whether it be maybe some of you are familiar with geographic information systems, so it could be a geographical layer on which things happen. So one mnemonic, one kind of simple way to think about agent-based modeling is it's agents plus an environment is going to be the model. Okay, you guys are too young to remember, but when I was a graduate student, a very popular book in computer science was Professor Nicholas Wirth's book called Algorithms plus Data Structures equals Programs. And so we have a similar kind of idea here. Agents plus environment makes agent-based models. By the way, I should also mention that I was interested to hear that many of you are engineers from the business community also. My first degree is engineering, and then later on I studied economics. So I think that people with heterogeneous mixed backgrounds are in a good position to leverage this kind of technology since it does involve some programming. Okay, here's a very simple agent-based model. I want to describe it in detail. It's the first one I ever created many years ago. So we have obviously a grid here. It's 50 by 50, and the yellow stuff is a kind of food that the red dots like. Okay, and the more yellow it is, the more food that's there. Now we didn't know what to call this notional food, so in the end it became known as sugar. This is the Sugarscape model. The yellow background represents how much sugar is present. So there's not very much sugar up here where it's white. There's more sugar in these two areas here, and kind of a sugar desert in the middle between the two. And then the red dots are the agents. Agents are going to have a very simple behavioral rule here, which is going to be look around your own local area, find where the most sugar is, go there and harvest the sugar. Okay, so they're all being fairly greedy here. They're all going to do what's best for them, trying to do what's best for themselves. They're all going to try to, rapaciously, as it were, consume all the sugar. And then the sugar is going to grow back. So think about the sugar in kind of integer values. There's no sugar out here. There's 1 unit of sugar here, 2, 3, 4, 5 in the center. So imagine that a red agent harvests the sugar from here. Then there's going to be no sugar left there anymore. And so over time, though, that sugar will grow back, 1 unit at a time. So we're going to march this model forward. Maybe some of you have done discrete event simulation or discrete time simulation in the past. Every time period, every red dot will get to move and forage and find some sugar. Every period of time, the sugar sites will get to grow back to some sugar up to the capacity you see here. So no sugar can ever grow out here, and sugar can grow here, but only to a small extent. And sugar can grow to a much better extent here. Okay, so when we turn this model on, we're just going to see the agents, each one sequentially in some random order, following their behavioral rule, that is, go around and harvest the sugar. Now, unlike a conventional mathematical model or computational model that I would have learned in engineering school, this model does not produce an answer like 42 or pi or something, right? This model is, when we turn it on, it's just going to come alive, as it were, with the agent motion. So I think there's about a minute or two of a movie here to watch. And what you immediately see is, the agents are on this landscape. They're moving around. They're trying to find where the most resources are. You can see in some of the areas where there is lots of capacity, the sugar is taking time to grow back, so there's some places where it's more white than yellow. These agents are the ones who are lucky that they were born out here. Well, they're lucky in the following. They're unlucky in the sense they were born in an area where they can't, where there's only a low amount of sugar. But they're lucky in the sense that they don't have much need for sugar, so they're perfectly content to stay right here. What I didn't go into in detail, but I'll mention now in a little bit more detail, is to say that these agents are heterogeneous. That is, some of them have need for a lot of sugar every period, and some have need for only a small amount of sugar. So these people in particular didn't need much sugar, and they're perfectly happy out here. Some of the ones in here need more sugar, and so they're going to be trying to find all the sugar they can get their hands on. It's also the case that none of these agents can see the entire landscape. So, many times in, say, in economics, we have mathematical models where agents know all the information about the economy. They know all the prices. They know, and we say, what is the rational thing to do? The agent can do the best thing for itself. In this kind of modeling approach, we typically have agents with limited information, and I'm going to talk more about that in a minute. Limited vision. So here, I said each one looks around in its own neighborhood, and it finds where the best sugar is, and it goes there. Now, these agents, who are in essence stuck out here in the periphery, they can't even see that there's more resources here. So this agent can't see here or there where there's more resources. It has a small vision, it's stuck out here, but it can survive out on the periphery. I'm going to run this again and just talk through this from a different point of view now. The point of view I want to suggest, maybe from a more business management side of the equation, would be something like, imagine this is a farm that you are in charge of. You're the manager of the farm, and you have these, a couple hundred agents who are going to be your workers. Now, you could try using some very complicated mathematical programming techniques. You could try to figure out an optimal harvesting plan for this landscape, knowing how it grows back. You could say something like, give every agent a number. Here's number 1, 2, 3, whatever. So you could say, okay, agent number 37, you go to spot, 45, 25, whatever, at time 6, and then a different spot at time 7, et cetera. You could, for all the 200 agents, try to compute an optimal harvesting plan. And that's going to be obviously a lot of work to do that, right? It's going to be hard to do that. The alternative is, if we just give the agents a very simple rule that they can use local information with, they can look around and decide what the best thing to do is, it would then not be incumbent on us as a manager to have all that information, right? So there are times when we can, in essence, decentralize the decision-making by letting the agents use their own sensing ability to figure out what the best thing to do is. So I just want to provide this as kind of a, maybe not a very realistic dichotomy, but just to say that this is an example where to do something from the top down, that is, figure out what is the globally optimal harvesting strategy, is going to be a computationally very difficult problem. Whereas just giving the agents, in essence, what we have here at the moment are greedy rules, we can get very high harvesting rates. And now, it turns out I wrote an entire book about this model many years ago, published by MIT Press. We go into more detail there, and I won't bore you with it right now, but except to say that if you look here, you will see that there are very few high sugar sites, if I pause it, that go unharvested. Like, if you look here for a second, we say, okay, if those small dots are places where the sugar has not grown back all the way yet, the big dots are where the sugar has grown back. If you watch, I'll click at just one period, we can watch one period go forward. These places where the sugar is rich are not going to survive very long. Those places are going to be quickly harvested. Right? The places where the sugar is rich, right there, if we go forward one time period, that's going to be taken immediately. So in essence, we go into more detail in the book, but this is a very efficient harvesting strategy, and the key terminology I want to use is, this is from the bottom up, right? We're saying from the bottom up, there emerges very efficient harvesting of this landscape, even though there's no top-down control. So is that everybody okay with that terminology? A different way to say it is we might say, there emerges from the interactions of the agents efficient harvesting of this landscape. So emergence is a little bit of a code word in complex systems to say, even though there's no top-down control, even though no agent knows everything, even though we have you guys, by watching this, you have the God's eye view, so-called, of everything going on. Remember, no agent can see what you can see. All any one individual agent sees is what's going on in this local environment, but we can still get high performance in some notional sense here from this. Okay, everybody okay with that? So just a high-level discussion of implementation, and you're going to see in the next couple of days, people each have their own, our typical programmers will have different ways to do implementation, but at a very high level, it turns out that if you're going to use a programming language where there are objects, so-called software objects, object-oriented programming, then it's very convenient to represent agents as objects. And if that terminology sounds foreign, don't worry about it. But if those of you who know what object-oriented programming is, you'll understand better the assertion. It turns out we can also make the entire population of agents can be an object. And then you can do things like you can say, for the population object, I can write a method for saying, give me the statistics of that population. What's the average sugar income? What's the average vision of the agent, something. We can make each part of the environment, like each part of the landscape I just showed you can be an object, and then the entire environment can be an object. So object-oriented programming is a natural way to implement all this. So just once again, stepping back, I'm looking at the last 25 or 30 years of my career. I think that kind of, when we first started building these models, objects were a new thing, unclear how to use them, but it's really been a kind of a co-evolution of agent-based modeling with object-oriented programming that's made this all this relatively easier than it would have been otherwise without these ideas. Maybe the final thing to say, and this is just the way I do agent-based modeling, I'd like to say that once I have an agent object and I have an environment object, I then will just, by composition, make an ABM object, and then I can have a Sugarscape object, which like the model you just saw. Okay, so this is implementation, high level. You'll see details about how people do this in Python, or maybe in Java, or in C, or C# or something. You'll see that over the next, in other discussions. What I want to go back to, though, is the idea that when we look at a model, when an agent-based model runs, it's not just that we get some kind of visual output, but the model's doing something that we care about. In this case, you would say, well, what could we possibly learn from that very simple model where heterogeneous agents forage on a landscape for resources? Is there anything that can be learned? And I'll just report the fact that already with that very simple model, it's somewhat surprising what arises here. This is a histogram of how many resources the individual agents have. So the vertical axis is a count of how many agents there are, and there's something more than 100, maybe a couple hundred agents here if you add them all up. And it says that at time 0 in the model, nobody has more than 30 units of sugar. So basically, they're all born with some sugar, and over time, they're going to accumulate more sugar. Now, some of them have high metabolism, need a lot of sugar. Some have low metabolism, only need a little bit. And so you're going to see these things change over time. But for those who happen to have low metabolism, but maybe they're born into the area where there's a lot of sugar and they can forage successfully there, they're going to be able to accumulate sugar. So I'm going to turn this on. You're going to watch it go, and so a very, very simple metric for what's happening in this model is to say, well, let's keep track of how much sugar. I've written here sugar wealth. How much sugar is present in the population. Now, I didn't go into the details. The details don't really matter for what we're discussing here. But basically, when agents harvest the sugar, it's like they put it in their backpack or they put it in their bank account, and they can just hold it forever. It doesn't decay. They can eat it whenever they need it. But notice though what's happened over a very short time, and this is for the run that you just saw. That's the same model run. That at the upper end, we're getting this progressive accumulation of resources, and there's this, there are few agents with a lot of resources, and the progressively larger numbers of agents with progressively fewer resources. So this distribution of income or wealth, would be qualitatively, not quantitatively, but qualitatively like things you would see in a real human social environment where, there's going to be an upper tail to high income, high wealth, and there's going to be a lower tail that we care about too. Now, for those of you who have done economics, you may have seen these kinds of distributions represented in a different way. This is the so-called Lorenz curve, where basically what we do is we have the population ordered here from the poorest up to the wealthiest. And so if we accumulate how many resources they have, that's going to be this line here. And it says that the way to read this is, the poorest 30%, say the poorest, say 25% of the population's got about 10% of the total sugar wealth, and then the poorest 50% has something like 32 or 35% of the total wealth. All right. So this line refers to the actual distribution of wealth in the society. This 45-degree line would be if, in fact, the poorest 30% own 30%, then you would have the 45-degree line, etc. So this would be a perfectly egalitarian society. This is an inegalitarian society. And you could imagine if it was the case, if this line was not shaped the way it is, but if it was shaped more like hugging this horizontal here and then jumping up suddenly, if, for example, say the poorest 70% only own 10%, that'd be a much more inegalitarian society than we have showed here. So in some sense, the gap between the black line and this line refers to how much inequality there is. If there was no gap, we'd have an equal society, and if we had as the gap gets bigger, it's progressively less equal. So what we saw here when this just ran, it started out to be relatively uniform, but it grew to this skew structure. So when we watched this, the evolution of this Lorenz curve, so-called, Lorenz was an American professor of economics 100 years ago or so. First wrote out this kind of formalism. You see basically, the growing white space, the decreasing pink volume here. And so this society is becoming more unequal over time, and we saw that here. And it turns out that the Italian, well-known Italian statistician Gini first described, basically, if you look at what is the ratio of the white space to the entire area of the triangle, that's called the Gini ratio, right? And so the more the white space, the more unequal, the higher the Gini ratio. So, and some of you may know, I actually don't know what the data are for India, but for the US income, not wealth, for US income, 0.45 is not unreasonable, typical number. For US wealth, it's much more skewed. For US wealth, it'd be something much more like this, and the Gini would be closer to 0.7 or in that range somewhere. So anyway, I guess my main point is not to have a digression about income and wealth, but rather just to say that this is an example of looking at the output of a model and trying to relate it to the real world. Here, even if it's a toy, almost trivial model, we already get things like skewed distribution of income or wealth. Now, the question that might be, the obvious question to ask, I suppose, is why do we get skewed distributions of income and wealth in such a very simple model? And that is, in fact, the $24,000 question, as it were. But in essence, just to summarize quickly without going into details, we can talk more about it at the end. Because the agents are heterogeneous, some have need for more sugar and some have need for less. So they have heterogeneous metabolism, as it were. Because they have heterogeneous vision, some can see that there's resource-rich area here. Some on the periphery can't see that there's a resource-rich area there. Because they're heterogeneous, and also because some are born into the resource-rich area, some are born in the resource desert. All those things accumulate to produce an unequal distribution of income and wealth. Okay, so we can come back to that at the end. What I'd like to press on and do is talk about, now that you've seen this example, is to go through this, and I apologize right now for it being busy, but I'm going to explain part of it. This is a table from a paper that I have just published in the Journal of Economic Literature. Now, I'm an agent-based modeling specialist, but I work primarily in economics and finance. Some of you have training in economics and finance, in economics, say. So I think when we build models, whether in business or in government or in economics, in finance, we typically are going to have all of the, some subset of these things that I've written here on the left-hand side. How many agents are we going to model? It's a monopoly. We need to have one agent. It's an oligopoly. We need to have two, whatever. How diverse are they? What are the beliefs of the agents? Are we going to have a market model, yes or no? Are we going to have a regulator in the model, yes or no? How does the model evolve temporally, if it's et cetera. So a whole variety of features, which I'll go through in a minute here. And it turns out, for those of you who have done graduate level economics, if we make a whole bunch of very strict assumptions about what these things are, for example, we say, well, if it's a monopoly, we will have one agent. We're going to give the agents a fixed utility function. They're going to maximize that. They're going to have all the information that they need, and they're going to be, an auctioneer is going to clear all the markets. So by making a series of strong assumptions, everything is differentiable, all the dynamics are smooth, we can basically solve a wide variety of problems in business, economics, finance, etc., when we make these strong assumptions. Now, the obvious, I think, thing that, of course, for those of you who have sat through graduate level economics, is that probably your first impression is that you kind of have to hold your nose that these assumptions are so strong they may not be right. And so if they're not right, then how good are the results, right? So you hold your nose because you don't really like the assumptions. I think those of you with training as an engineer, you may say, well, if the assumptions are so strong that they're unrealistic, is the model any good? Maybe not, right? So I think it's fair to say that there is widespread understanding among economics, people who do economics research, that the whole point of this is not really that it's realistic. It's simply that it's a point of departure. We know how to solve this one. I've written here that things like, think macroeconomics. We have a microscopic level, we have a macroscopic level. We solve for equilibrium. These are all things that you do in academic economics. The whole point of doing economics research is we like to have more realistic things. So we'd like to move over to what I put here on the rightmost column, and this is, instead of having homogeneous agents, or maybe a few types of agents, let's make agents heterogeneous, like I've just shown you in the model. Instead of having people who are always rational, always doing exactly what's best for themselves, I'll just stop for 1 second and say, I spent many years at a policy think tank in Washington called the Brookings Institution. And I had a colleague there whose wife was a psychotherapist, so-called. And he would always joke that when he would tell his wife that he was modeling rational agents who do the best for themselves, he said his wife would always say, that's a passable definition of a sociopath, right? So someone who doesn't even care about what their family happens to their family or their siblings or anything, they're just doing what's best for themselves. So, I mean, instead of a rational agent, we need to have agents who are, adaptive, yes, but they're probably biased and myopic, et cetera. Today we have the whole area of behavioral economics is dedicated to ways in which people are not just rational, for example. I'm going to discuss in a minute that oftentimes information is not uniform across the population, but it's distributed. Some people know more about this than the other thing. Some people know about copper prices, other people know about IT prices, something, right? And it might even be the case that the knowledge that you have about how you do your job, you can't even tell the person who's coming in to replace you as you get promoted, because your knowledge is tacit, right? Your knowledge it's part of your own being and part of how you're going to interact with your technology. So there are a whole variety of ways we can make models more realistic. We can have them be, instead of just micro and macro, we can have them be multi-level models. So I'm going to talk about some of these things in more detail. We could spend the entire day talking about this table. The main point to say is that we'd like to move models in the social sciences, in economics, in business, in finance, et cetera, over to this column. But the trouble is, no one knows how to do that mathematically. Nobel Prizes have been awarded to Samuelson, Solow, Arrow, for trying to do something over here. I mean, arguably, just getting this all to work out has been the subject of many Nobel Prizes. And then as we try to relax these heroic assumptions over here, it's very hard to do that mathematically. I'm just going to assert that. We can talk more about it in a bit. Now, for me, personally, the main punchline of this table is that when it comes to agent-based modeling, the rather remarkable thing is we can turn on every one of these things. We know how to there are models with every one of these things to, there's a paper, for example, which maybe does a lot of this stuff, but then it will turn on like maybe this and this and this. So it's possible computationally to make progress where it's difficult to do mathematically. So say you're in business, you want to model a supply chain. You say, well, in the supply chain, I really care about the network a lot. I have to know who the suppliers are, et cetera. I don't want to assume that I'm just buying inputs off the spot market or something. So you'd like to build a model with this turned on. Well, there are models like this. So one of the powerful things about agent-based modeling is that we can turn this stuff on. One of the risks in agent-based modeling is you might turn on too much stuff, and you might say, I think I'm modeling my problem with high fidelity, because I got these important things turned on, I'm just going to assert the fact that it may be, though, that you set off sailing for the new world, and you end up in a different part of the world because you're not really sure where you end up. Are you modeling your company, or are you modeling a slightly different company because you turned on things that, what is the underlying social network? Is it a lattice? Is it a small world network? Is it a power law network? There've been a variety of things, and if we may not have a lot of data on this. I'm going to go into detail about that in a second. The main thing I want to say is that, when I write the social sciences are hard, I mean, we all know we want more realistic models. The ones that we learn in graduate school are not that realistic. We don't know how to, it may take hundreds of years for the mathematics to progress to this area, but the good news is we can do it with agents as long as we're careful, as long as we do it with discipline by data, we can turn on the things that we care about. And I'm going to give you an example, give some examples here directly. For example, it's already been discussed that there's some connection between complex systems ideas and agent-based modeling, also Austrian economics ideas. And so one of the early economists who described the fact that information in a society is really distributed, not centralized, was Hayek. And so I'm going to talk more about that in a second. There's a whole bunch of things over here. When I was in graduate school, I worked with a man named Herbert Simon who had ideas about rationality being bounded. There's a whole bunch of things over here we can go through in detail about all of them, but I'm going to talk about just about 5 or 6 of these, okay? And so for these 5 or 6, it turns out, there is fairly well-defined work that says, yes, the kinds of models you get when you turn these things on look different than when you just use the usual assumptions. And so what I want to do now in the next, say, 15 minutes or so is just walk through these kind of one at a time and say, how might it be the case that when you turn some of these things on that we know are more realistic, you can get a different answer in your model. And the last one I'll talk about is policy for part of it. All right, so first of all, distributed information. In your managerial economics textbook, say that you did when you in your master's degree or something, there were prices that were just given, and then it was said that how do agents take a good decision given that they have this set of prices? Now, Hayek said, well, there may be parts of the economy where the prices are a certain thing, but in a different part of the economy, the prices are different because, for example, maybe it's a price of a natural resource, and there's been natural resources been discovered nearby or something, and that's modified the prices. So it may not be, in fact, that there's one price vector that is going to be obtaining throughout the whole economy that you can use for decision making for all agents. So Hayek's famous paper discusses this in detail, and he also discusses the fact that I've written here, no group of people has enough knowledge, enough information about the whole economy to, in essence, make that economy work properly from the top down, as it were. This may seem like an old idea, but I mean, maybe there was a time when this was a contentious idea. Today, we know the economy is so full of information, it's so distributed, decentralized that it would seem odd, I guess, to think that a small group of people would be able to design the economy from the top down. And then I mentioned already tacit knowledge, the idea that sometimes certainly there are going to be cases where people who are working on manufacturing something have very intimate, detailed knowledge of how to do their job properly, and they may not even be able to communicate that well because they've been doing it for so long, and so that we sometimes call this tacit knowledge. By the way, I'll just mention I think a fun little footnote here is that because tacit knowledge is something that you say, well, it's very hard to formalize. What does this even mean? I've been on a couple research review panels where people have proposed research on tacit knowledge. And everybody on the review panel always starts out saying, it's a very important thing to understand tacit knowledge. We should do research on this, and yes, we should fund this proposal. And then after about 5 or 10 minutes of talking about it, people say, yeah, but these researchers want to think that they actually think that tacit knowledge is this or that or the other thing. And everybody says, well, the whole point of tacit knowledge is that nobody knows what it is. So how can you possibly model it, right? So anyways, I think every time I've been on a committee where somebody has proposed studying tacit knowledge, the proposal always gets shot down because nobody can agree on what the heck it even means. But certainly is an important thing, and one reason why we want to have even if we don't know how to represent this properly, we at least want to have models where we don't have centralized knowledge. Okay, on to, I mentioned boundedly rational behavior. People are myopic, people are biased, people are not fully rational. For an agent to be rational, we need to have complete information and possibly a huge amount of computing. And it was Herbert Simon back in the 50s who said, people face real constraints. So one of the things that we're going to encounter with agent-based modeling is that, we're never going to be able to give one of our agents infinite computing, right? Because we don't have that available to us. Agents always have to do limited computing with the information they have. And so we're going to, in some sense, be forced to do things that are more realistic than what the first bullet says. By the way, just as on the first bullet, if you don't really believe what I've written here, some of you may know that in the current the current crop of macroeconomic models used by the central bank, it is assumed that the representative agent has rational expectations, and what that really means, right, is that that agent has a correct model for how the world's going to unfold, and so that in some sense that agent has an accurate understanding of how the world works economically, and so you could ask that agent, are we going to have a recession, yes or no? Are we going to have volatility in the markets, yes or no? I mean, in order for those things to work, we have to have this kind of omniscient agent, which is not credible. It's not credible. Computer scientists proved in the 90s that in fact computing prices that clear markets I'm going to do some hand waving here, we can discuss it later, essentially an NP hard problem. It's among the hardest problems in all of computer science. It's not credible that any agent, auctioneer, could actually compute the prices that would clear the market. So of necessity, and once again, I'm kind of slogging a dead horse here, of necessity, people are doing simpler things than trying to compute the optimal thing globally, because it's just too hard to do that. And of course, modern behavioral economics, we know that people, we put people in laboratory settings and they reproducibly do things that are not optimal. And we can talk more about that. If you haven't encountered that before, we can talk more about that. Okay, let's go on to path dependence. My colleague at the Santa Fe Institute, Brian Arthur, has talked a lot about this. From a mathematical point of view, we would say that any kind of system that's Markovian, right, it just kind of runs forward in time, it reaches some steady state, and then it doesn't matter which path you took, you're always going to be in the steady state. But Brian Arthur and Paul David talked about, look on your keyboard. Many of you have your keyboards open. Actually, I'm not so sure about Indian keyboards, but across the top of my keyboard it reads QWERTY. Right, the first rack of letters QWERTY. Why? Well, why QWERTY? And the argument was that in the first mechanical typewriters that came around 150 years ago, is that those mechanical typewriters, you had to have an arm go up and hit the paper and leave the imprint, right? And if those moving arms, one for every letter, would move too fast, they would get jammed, and typewriters would jam. So the argument about QWERTY, and there's a more subtle, nuanced argument that we understand today, but the coarse argument about QWERTY was this was actually a design which produces very slow typing, so the keys won't jam. So you say, well, okay, if this is designed for slow typing, why do we still have it today? Why are we still using the slow keyboard? And the answer is we're just locked into it. Everybody learns it, and some of you may know there are alternative designs. There's a Dvorak keyboard that runs faster, et cetera, et cetera. But the main thing to say is this is an example of, potential example anyway, there's been some debate about it, potential example of you're locked into an inefficient technology for reasons of historical precedent. And there are many other examples of this. I think that even some in India about different railroad companies have different so-called gauges, width of the track, so that some trains can't run on all different companies' railroad tracks. And so in general, technology standards have this property that you kind of lock into them. Now, if they evolve over time, that's one thing, right? We can change the connection on a USB overnight, that's fine. But it's very expensive to change the railroad gauge, right? Are you 3 feet apart or 3.2 feet apart or whatever? And so when the path matters, you can't simply solve for what is the equilibrium of the thing you're looking at. What's the equilibrium of my supply chain or something? Because there can be multiple equilibria, and the equilibrium you arrive at may be determined by where you start, right? The initial condition may matter, right? The first railroad builder picked this gauge. Well, that's not the best gauge for the modern railroads. The locomotives are too heavy or something. You rather have that gauge, but you're locked into the narrow gauge because the early railroads are not so big. Anyways, you get the idea. This is the kind of thing though that's somewhat hard to model, mathematically, statistically, but we can do it with agents, and I'll give some examples. Okay, on to I've written here governance. For those of you who have done some macroeconomics, you may remember that in the same way that in macroeconomics we have a representative agent who does the best thing for the economy, this is kind of like a benevolent social planner. Contrast that with how things work in the real world. I mean, in the real world, there's some resource to manage. All of us are the users of that resource. We have to decide how to govern that resource. This is self-governance. Elinor Ostrom, who won the Nobel Prize about 10 years ago, she pioneered much of this work. The social planner's perspective is from the top down, maximize welfare. Ostrom says no, that many natural resources are governed from the bottom up. And she has many examples of this. Some of you may know in this book, there's discussions of water in Los Angeles, forests in Nepal, fisheries all over the world, etc. So she talks about how do people who are exploiters of some resource come to govern the resource so they don't ruin the resource, basically. And of course, she has examples in here where the resources did get ruined by certain kinds of bad governance. How does the governance arise? Is it stable or not? She has an example in here. One of the great examples in here. She has there is a set of rules for how Japanese certain villages in Japan, high in the mountains, who use wood for heating, and what the rules are for gathering wood from the forest, and how no individual family is allowed to take too much wood because there's a box, let's say the size of this table. They have to keep the box in front of their house, and so everybody in the village can see how much wood is in there. Now that set of rules for exploiting the forest in Japan have been in place for more than 1,000 years, and they are robust to things like changes in climate, which cause the trees to be more or less to produce more or less dead wood that can be used. So, anyways, the main point to say is that these self-governance ideas are much more about how could a system of agents learn to govern themselves, as opposed to simply saying there's a social planner which dictates how things would work from the top down. I'm getting to the end here about this discussion. On social networks, when I was a graduate student 25, 30 years ago, there was no work on social networks. Today we have textbooks on this topic. The main thing to say is that human interactions are not according to equal probabilities. I mean, you interact much more with your family members, with your coworkers, etc. So we want to have some kind of network in which will mediate the interactions. And I've already alluded to this in the case of an age-based model is a set of agents plus a network. We have a lot more data on these things than we ever had before. And some of you may have, for example, followed that during COVID, trying to understand who was interacting with whom and how the COVID virus, how the SARS-CoV-2 virus was being transmitted. There was a large effort to understand contact networks, et cetera. This book is a great introduction to this whole topic. And one thing I will say at the end of Matt Jackson's book, what he says, look, in my book, I'm paraphrasing now, in my book, I've discussed how for idealized networks, idealized systems, we can use mathematics game theory. But if you get into any kind of realistically complicated network, you probably have to use agent-based modeling. So that's how the book ends. Okay, last one, policy. And we'll talk about policy at the end of the day tomorrow. And I've just written here where the traditional policy approach is that the president or the king decides what the policy is, and it's instituted from the top down, and everybody follows the policy. In reality, parliaments, Congress, local jurisdictions figure out the policy. The dean mentioned recently, a few days ago, Professor Vipin and I and other people were up in the mountain region where we're looking at animal-human conflict, and policies that are going to solve that problem are going to be ones which the stakeholders buy into, right? The stakeholders being the farmers, the tribal people, et cetera. And so instead of just being told what to do, policy will come from the bottom up. There's been good discussion of this in the literature. There's this recent book called by Colander and Coopers about instead of a social planner doing policy from the top down, real world policy is enacted, much more evolutionary flavor, and there's a close connection between agent-based modeling and complex systems and this approach. So I've given several areas in which several examples of where we can use agent-based modeling to build richer, better, more realistic models. But at the end of the day, and I just step back for a second and say, it seems to me this is where your country is very well positioned to make a big splash in this whole area of complex systems and agent-based modeling. Is that at the end of the day, I think the ultimate advantage, the ultimate reason why there will be much more agent-based modeling going on in the year 2030, 2050, 2100 than there is today, is simply due to the fact that we have this incredible growing hardware story, right? So this is a plot of a variety of things over time series plot. And by the way, it only goes to 2015. I had the data for up to 2025. It's the same story. The number of transistors has been growing exponentially on each die. Really, this is Moore's law. So the red dots are Moore's law. Everybody's heard about things the whole hardware world is changing and Moore's law is slowing down and everything. But in reality, the number of transistors is still growing exponentially. Okay, this just gives some specific technologies that have been in play. What has been plateauing is you can't put any more power into the thing. You can't make it run any faster because you can't get all the heat out of the chip. So those things are plateauing. And so what's plateauing then, because this is plateauing, is the performance of the processor. Now this doesn't really matter whether you're talking about GPUs or CPUs or even hard disks and everything. We've seen this kind of plateauing going on, but as many of you know, in fact most of your boxes I'm sure have many cores on them. So notice that as the frequency as these various performance metrics have plateaued, we now have the number of cores going up. These are miniaturized further, right? And so the dies are not just getting giant, but the dies are growing in size, but you get getting more cores. So with the rise of parallel computing, you can still get more and more performance. So as long as you can take advantage of these cores, the performance can keep growing exponentially. As a footnote, I'm just going to wave my hands on this so we can discuss it more in the time we have for a discussion, is that agent-based models are quite naturally parallelized. Unlike natural science models where usually you have to jump through a lot of hoops to do things, my own research group has spent about 5 or 6 years getting very good at this. And so, but when you think about it, if I have a big population of agents and I have many cores, all you got to do is you just break the population up into small pieces, put each piece on its own core, let it run for a second or two, a few seconds, and then just mix the agents again, redivide them, repeat the process. So models that used to take us 2 days or 3 days or 4 days to run, and I'll talk about some of them tomorrow, when we put those models on a box with, say, 24 or 48 cores or 100 cores, we can get almost linear speed up. So a model that used to take, say, 48 hours to run, on 10 cores it runs in 4 hours, on 100 cores it runs in 45 minutes, kind of thing. Right? So I guess the main thing to say is that, look, mathematics, we need to make progress in mathematics to get to the right-hand side of the table that I showed earlier, for business problems, for economic problems, for finance. Progress in mathematics is not growing exponentially fast. At the moment, fortunately for us, progress in computing is going exponentially fast. We'll be able to take advantage of this. When I first started out programming, I showed you that Sugarscape model. That was my first agent-based model I ever wrote. That has got a few hundred agents on it. Today, we build models with millions or hundreds of millions of agents. And I'll talk about some of them tomorrow. Okay, so the summary of this is that agent-based models are a fresh way. I was going to put new here, but I've been working on them for 20 or 30 years. And so it's a fresh way of doing things. They have some advantages over conventional approaches, and I've described some of them. I think you're going to get over the next couple days, over the rest of today and tomorrow, you're going to learn about certain tools and techniques for building these in software. I have purposely not shown you any software, but I'm happy to do that if there's appetite for that tomorrow. And of course, when I teach agent-based modeling, we spend almost all of the time is how to create ABMs in software. That's the main thing we work on, of course. And so tomorrow I'm going to discuss applications to problems in, say, academic problems. Can we build better macroeconomic models with ABMs, for example? I'll describe commercial applications, things like, some of you may remember about 20 years ago, the NASDAQ financial market used to trade in eighths and sixteenths of a dollar. And then the American SEC, so-called, the Securities and Exchange Commission, required that they decimalize the market, go to pennies. And the people who ran that market were unsure what effect that would have on overall volatility and price discovery, et cetera. And so they successfully negotiated with the SEC to spend for a 1-year delay in getting that market, in decimalizing the market, while they explored what would happen to the market upon decimalization. And basically they hired a team of complexity researchers, which I was on the periphery of, to build a high-performance, high-fidelity ABM of how the NASDAQ market works using their proprietary data. And so that was quite a successful project in which the ABM, before decimalization, made a forecast of that 7 or 8 things were going to change structurally in how the market worked. And all of them, except for one, were borne out when the market finally did decimalize. So this example where you can use these things for policy. And I'll go into the details on that tomorrow. So with this, I've taken up about 45 minutes. I think I'll stop here, and we have time for a few questions. Thank you.
So Rob, how do you decide how many agents we have in a model, and how do we decide the population, and how much does it matter?
Great question. And so in the old days, especially, when we couldn't do large numbers of agents, we always faced this question. We would say, there's some social phenomenon, we want a model that has 50,000 agents, but we really can only do 1,000 computationally, so we always had to face that issue. I think these days now, the good news is that we can almost always do things at scale, almost always. Here's a very simple example. I'm going to show you guys tomorrow a model of Disneyland, which is the smaller of the 2 Disney parks in California, in the U.S. and what's the one in California. And at any given day, there are about 50,000 customers at Disneyland. And so when we first started doing that model, we really could only model it maybe at 1/10 scale. But these days, it's very easy to do 50,000. So I'll just assert that for a wide variety of models today, the right answer to your question is just do it at full scale. But there's still going to be times when that's not possible. I would say this, that we don't really know a ton about when you scale things back, how much bias or does that put into your results? How much does that kind of, in essence, corrupt the scientific understanding? We don't really know that. I've had a couple of PhD students start working on that problem, and I would just say that there's a little bit known, but not enough. I'll report the following, that one of the things, maybe also discuss tomorrow, is one of the things that's going on right now in the economics sphere is a bunch of central banks really believe that housing markets oftentimes cause them problems. And so, and there are several countries right now where the major city in the country, which is often, by the way, where the central bank is located, those cities are probably going through some kind of housing market bubble right now. And so, for example, I'll just report the fact that there are back when the US experienced the housing market bubble in 2010, we built a model of the entire Washington, D.C. area. And we did that at full scale, but then it was quite expensive to execute. But Washington, D.C. is a relatively small city with only about 1 million housing units. So these days, the central banks in England, Norway, Spain, Italy, Hungary, Australia, and one Asian country either have or have started building high-fidelity models of the housing markets in their major city, London, Budapest, et cetera, Oslo. And I'll just report the fact that so those models are full scale in the following sense. They try to represent every house that's for sale, every household, or every house that exists, whether it's for sale or not, every household, and then every mortgage is the key. Every mortgage. Now, some of those models are data intensive and have been run at less than full scale. And so there is a brand new paper out by the Hungarian Central Bank on what is the effect on their housing market model when they run it at different scales. So that's a good answer to your question. But I don't think we have a general answer for agent-based models, overall. But we have some of these specific ones. And of course, one of the good things is, one of the, I think, maybe a different way to answer your question is to say, imagine that I run my model at whatever scale and I get out some result. One thing that's relatively easy to do is to run the model then at, say, half that scale or twice that scale and see, do you get something out that looks about the same or not? If you get something out that looks quite different, then you're worried about what is the right scale. But oftentimes, you can gauge to what extent you need to worry about it by simply trying a little experiment and seeing what happens.
Thank you for the exciting and so much of learning in the talk, and looking forward to the session tomorrow. I have a few questions about the way you did the modeling earlier times when you have 120 million agents for a model. Right now it seems doable, but when you did this, how did you manage to do 120 million agents in the compute we have?
So the question is how on some of the very large scale models, we're able to run them and get results out, say, that were reasonable. I think that the only reason, okay, so here's the quick background is that I do have a model running. I've been working on it for several years now, which is currently at the moment a one-to-one model of the U.S. private sector, which is there are 6 million firms that have employees. Those 6 million firms employ about 120 million people. Now, it turns out when we first started that model, we could not do things at full scale. Over time, though, the computing power grew, in the way I described, and we got very smart about how to do parallel programming. It took a while, so we can now run that model at full scale. I'll say this, that in the case of that specific model, we had very detailed data on all the 120 million workers, very detailed data on all the 6 million firms. So basically, from the U.S. government tax authority, we received their proprietary data in some anonymized form. And so I guess what I'm essentially saying is that we only really dared try to build such a large-scale model because we knew what the targets were very crisply. If we had just started out and said, let's build a model of the whole U.S. economy and just see what happens, well, we wouldn't have known how to do that. We wouldn't have known what the right targets were. But because we had detailed data about firm sizes across all firms, firm growth rates, firm ages, firm lifetimes, and then the conditional things like, how does growth rate depend on size, et cetera. Because we had all these detailed data, as we built up that model, we were able to make sure that the models stayed quite close to the empirical data. I think if your boss comes to you and says, we have, this very complicated supply chain, build me an agent-based model of it. Unless you really understand how that thing works, unless you understand who all the major players are, unless you have some data about it, it's going to be hard to grow like a full-blown, accurate supply chain just from scratch without being able to discipline it with data. So I think the main reason why we did do it at full scale eventually is simply because not only could we do it because of the progress in computing, but also because the opposite extreme of a full scale model is only a one agent model. And those of you who do macroeconomics, you may know that the way a central bank works these days is with what's called a dynamic stochastic general equilibrium model, DSGE model. That has one representative consumer or one representative firm, say, and so obviously with one representative firm, you can't address all the heterogeneity that's present in the real world. And when you think about American firms, I'm sure that I know it's somewhat true in India as well. There's such enormous heterogeneity from the giant Tatas and Amazons, et cetera, all the way down to the small vendor on the street, I mean, yes, they're both firms, but they're so different seemingly in scale and scope that if you try to have what is a representative firm when you have one firm with 1 million employees and one firm with 1 employee? It's not obvious what it even means. So I guess in some sense, I mean, maybe in a slightly different way to answer the question is to say, if you can go to full scale, it's actually easier. And here's the concrete way to say that. The mathematical way to say that is as follows. Imagine that I'm running a housing market model as I just described at 1/4 or 1/10 scale. Are the results coming out of that housing market, like a bubble, for example, does that bubble have to be rescaled because I got the inputs at the wrong size? Is the volatility in the output have to be rescaled? So the short answer is yes. You have to rescale everything because everything is running at the wrong size. When you run at full scale, the output of the model should be the same as what the government is reporting the data are. So in that sense, it's easier to run at full scale. But now you have to just deal with the computing issues, and so you have to go to see Professor Vipin to learn how to do Python programming.
Thanks. Can I have one more question?
Yes.
So we run this agent-based models for COVID-19. We did try that and some other infectious diseases. But a big skeptic are the theoretical computer scientists. They say, how do you verify these systems? And you mentioned NP-hard, so and it is a hard problem for verifying such complex systems.
Yeah.
So how do you say your ABM is actually capturing the reality as you expect? How do you verify?
Right, and if you're working on a model for your boss at a company and a supply chain, he says, "How do I know it's any good?" That's always going to be the important question, of course. So, I mean, the case of COVID is a particularly problematical one because in that case, as you guys all know, right? I mean, before the virus has the chance to fully manifest itself, we had to make guesses about what it's going to do, and so when you have to in such an environment, it's problematical to actually know if your model is valid or verified. But think about what the alternative is. If the alternative is a statistical model, econometric model, by the way, even a neural network model, because neural networks are just exotic regression models. In that case, until you have a lot of data, you can't really do the statistics on it, right? So those models are inherently econometric, statistical, neural network models are inherently problematical in a new threat environment, right? We don't have any data. So what kinds of models would you want when you're in some novel environment? And the answer is you want to have some kind of mechanistic model, right? I mean, the reason why, for example, think about how is it that people who do weather prediction can show you the possible path of the monsoon when that specific monsoon has yet to go anywhere, has yet to hit anywhere. We don't have any data on that. And the answer is because other monsoons there is data on them, and that monsoon model is a mechanistic model, right? It's got conservation of energy, conservation of mass, et cetera, built into it. It's not a statistical model, it's a mechanistic model. And so the hope is, anyway, that by simply putting in the current initial condition, the mechanistic model will spin forward and give you, those spaghetti plots about where the monsoon might hit or whatever it is. Or in the case of the US, it's going to be the hurricanes hitting Florida. So the mechanistic model gives you a chance at getting that right. Agent-based models are a kind of mechanistic model. If you have the right mechanism in there, it's going to do a good job. Now, of course, if you have the wrong mechanism, it's not going to do a good job. And back to the COVID example, some of you will know that, the main model which drove a lot of policy around the world was that paper by Ferguson and his research group from the Imperial College called non-pharmaceutical intervention paper, right? Where he showed that if you did nothing, you would likely overwhelm all the hospitals would have more patients, more cases than they would have beds for. So the idea of a non-pharmaceutical intervention is, because we don't have a vaccine yet, we'll try these things like lockdowns or keeping the students at home or whatever. That paper was an agent-based model, essentially. It was built before the pathogen, in essence, the biology of the pathogen was well understood. So there's a lot of guesses in there. And of course, the results are going to be somewhat uncertain for that reason. But for anybody who says, that model's no good, the model was wrong ex post, today we could do a much better job. Well, of course, because we know how the pathogen behaves. And for people who say things like, I don't want to believe the model I have a better model in my head. I mean, if somebody wants to compare their mental model to your computational model, I think you're in better shape than that. I'll just report the fact that I run a weekly modeling seminar. I have for many years in my department on agent-based modeling. As soon as COVID hit in March, February of 2020, I turned that agent-based modeling seminar into a COVID modeling seminar. And so we had all the major models from around the world were presented every Friday for about 2 years. And so we saw every one of them. And we'd do webinars with 1,000 people on them, that kind of thing. My feeling was that, of course, there were plenty of bad models. The models that were purely epidemiology were oftentimes kind of closer to being right because we had experience with the Spanish flu and other kinds of things to build on. My feeling is that the economic models were actually quite poor because it was very speculative as to which sectors were going to get hit or not. And then those models oftentimes were scaled down too. Like, a model of the UK economy was written at the level of maybe only having like a few thousands of agents, not having a few million. So those are always scaled down. One thing that, but I think on the main point though, my main point I want to make is, what we saw very few of were people who were models that were both epidemiological on the one hand, as well as economic on the other hand, and having a high verisimilitude with what actually did happen. So I think even today, God forbid, imagine another pandemic hits. We have somewhat better idea how to manage it, but I think it's always going to be, until the pathogen's specific parameters are better understood, it's always going to be unknown how good the models are going to be. And just maybe the final point to say is that some of you may know this history. One reason why schools were closed, at least in the U.S. and other Western states, schools were closed because in the 1918 flu, that after the end of World War II, many middle-aged people, like many people who were aged in their 30s and 40s and 50s, who had children, were killed by that Spanish flu. And so in places where the schools were closed, that led, the non-pharmaceutical intervention of schools being closed, that led to less transmission to their parents. In the case of SARS-CoV-2, now it was not the middle-aged people who were the most vulnerable, right? It was the older people. So quite a different outcome. Anyways, if anybody wants to talk more about that, I have 100 ABMs on my machine here from those presentations, and I'm happy to talk about COVID all day. So, good question. Yes.
Do we have any self-learning, evolving agents?
Yes, so there are a variety of ways to use modern AI techniques in agent-based modeling, and let me go back to my figure here. For example, so when it comes to making agents, or adaptive, when we make them, how do they learn? I've written here they could be from AI. So there are, in fact, at the research frontier now, there are ABMs where the individual agents are using machine learning to try to understand how their environment works. Concrete example, Professor Blake LeBaron at Brandeis University has built models in finance where he has every agent is its own neural network. So then an ABM becomes not just one neural network, but basically a population of neural networks. And so, I mean, I guess one thing I did mention here out from this table, which I'll just mention right now, is that think about how you learned about economics. I've written here the ontology of modern economics is there are utilitarian, right? These are greedy agents who are going to optimize, do what's best for themselves. Contrast that with, in the ABM world, we simply say there is an ecology of purposive interacting agents. Now, in the case of Professor LeBaron's finance model, it's really an ecology of neural networks. So that's a very rich configuration. And now there are problems with some of these new models in the sense that we don't know, for example, we know how one neural net converges. We know how a few reinforcement learning agents can converge on an answer. What happens if you have a large population of neural networks all learning at the same time? It's not obvious how all that converges. So I think there are important research questions that are still open at the research frontier.
What are some of the most counterintuitive results that you have seen in your career?
Say it again. The most what?
Counterintuitive results, something that in your career through agent-based modeling.
Okay, so yeah, so purely counterintuitive. Let's see. So here's one concrete example. If anybody has ever traded stocks on the Nasdaq, have you ever been one of the day trader type people? You may remember there used to be this thing called the small order execution system, which for very small orders is a way you had to put your order in, etc. And then in the small order execution system, there was a very peculiar behavior where back when things were traded at eighths and sixteenths of a dollar, I think there's the people who are offering the best price to buy and people who are offering the lowest cost to sell, and so the gap between the bid and ask is going to be the spread, so-called, right? And so with small order execution, it's considered to be the day traders just take some relatively small stock, not a giant stock like an auto company, but just take some relatively small stock. There's a bunch of day traders working the bid price versus the ask price, whatever, and then what's considered to be bad behavior, but it's legal, is say that these people are trying to work this, it's moving up and down, going back and forth, and some big person comes in, somebody who maybe wants to trade 1,000 shares or 10,000, they come into the middle and just wipe out half part of the market. That's called a so's bandit. It's legal, but it's just considered kind of be bad behavior. Or at least that was the way it used to be. I'll just report the fact that when we first started building the Nasdaq model, it was completely unclear how to get this kind of so's banditry behavior in there. And then it turns out once we made the agents, once we gave them a little bit of an evolutionary flavor, so they could kind of learn what the best way to behave is. So we didn't from the top down say, this is going to happen. We just said, if you're an agent trying to make money, how would you behave? And it turns out we're in that model that I'll show a little bit of tomorrow, there emerged this kind of strange behavior of kind of jumping in and taking all the trades away. So that was an example where we didn't anticipate this was going to happen, and it just kind of came out of nowhere. Another example, maybe somewhat different character, is to say that many of you will know that in modern economics, it's believed that if the economy is in equilibrium, the only source of dynamism, in a model is going to be exogenous, right? There's an oil shock, there's a COVID hits, something, right? There are increasingly we see there are models where the dynamics are just a result of the agents doing things in the economy, right? Because the economy is not really at equilibrium, and you two guys change jobs, that causes some fluctuation in the output of your two firms, and maybe one of your firms makes a new connection to a new buyer or supplier or something, and so that you get endogenous dynamics, which, so 100% of the conventional theory is exogenous. I think that one thing that's emerging now in some of the macro ABMs is we can explain a lot of dynamism through endogenous terms, and that was not obvious when people started that work at all. That that you'd be able to get enough. And some of you may know there's, well, I won't get into the details, but so-called granular models of Gebecks and other people are relevant here. You want to talk more about this? I can talk more later. And there are other examples too, but I think maybe here's a somewhat different way to say it, is that one word I've not introduced yet, but I'll talk about tomorrow, is I talk to my students about agentization. That is, take a conventional model and just re-render the model with agents. I think when you do that, almost always you find something surprising that that was kind of swept under the rug in the mathematical model, say, but arises when you build it with agents. Yes.
There's one question on that sugar problem.
Yeah.
There are some agents, right, which stuck in their local environment.
Yeah.
They're not moving, even though they're not exploring the sugar, even if it is available in another wider environment. So why they are trapped in that?
They have too little vision. The resources are integer value variables, 0, 1, 2, 3. They have too little vision to see over here. So they can only see, in a radius around here. And so they're, it's because of the integer values, they basically can't, they can't see that far. That's all it is. Okay, yeah.
The local type environment for the agent, right? So
yeah.
Dimension is very limited, so they are not exploring beyond that dimension.
That's right, yeah.
So why it is designed like that?
Why did I design it that way?
Small dimension for each agent. Each agent has their own environment, right?
Yeah.
Small dimension. Beyond that dimension, they are not looking, exploring the environment.
Right. So, so I guess this may not answer your question, but let me just pose it this way. It definitely was the case when we built this model. I can just change one. I can run it with you afterwards. We can just change one parameter called what is the radius of the vision, and say, let's make it so everybody can see at least 10 units. If everybody can see at least 10 units, then we will never get this kind of behavior at all. So I guess this is just one particular set of parameters. I mean, I have no idea whether this would apply to anything realistic or not. But I thought it was interesting just that there was it just shows that there's different kinds of ways to survive in this world, either kind of like, living in the desert on a marginal, and maybe let me if I have just 2 more minutes, let me just mention one reason why I thought this was interesting was, and we put it in our book, was, I'm going to go find a different run now, was we did the following, which was, we said, well, one other run that's reported in the book was having to do with, what if we make it so that the grow back rate, so basically so that the way that the sugar recovers is not homogeneous across the landscape, but rather it varies somehow. And I'll be precise about it in a minute. See, that's not the one either. So I'm trying to think where it is. Maybe it's, no, it's not that one. I have to think about which animation is the right one. I don't think it's that one. So here's one example. We made it so that there were seasons on that landscape. So in the north, it would grow back slowly. In the south, it would grow back fast. And then every once in a while, it would flip to be the opposite. So there'd be seasons. And what we found was that there grew up then different ways to survive in that landscape. Some people were hibernators who just stayed. They could survive the winter. But there were other animals who had big vision who actually could go back and forth between the summer regions. And so that was just spontaneously emerged with enough vision, I guess. And so it was because we could see that there were multiple, even though we had agents who were just a kind of a broad cross-section of heterogeneity, different types arose based on what the environment was doing. And so for that one I just showed you, that had the flavor of just more of, there are different strategies for survival, and that was the main point of showing that, I think. So probably not a totally satisfactory answer, but I can show you the runs of that model later on.
Stressing more on the Sugarscape example, I think, is it right to say every agent in the model has incomplete information?
Yeah, that's right. Yes, they've none of them have knowledge of the whole landscape, for example.
Right, which is why there are outliers where they're not going to the concentric sugar.
Yes, that's right. Yeah, that's right. Yeah.
But when we talk about policy and governance, we claim that bottom-up approach is what agent-based modeling is working on. But when we bring assumptions like complete information and rationality, isn't it contradictory to a bottom-up approach than a top-down? And if you have an animation of the same thing with complete information, are the agents going to be placed in a concentric way with the concentration of sugar?
Yes. Right. Yeah.
Without
Right. So imagine we run this model where we give everybody if their radius of vision is much is much larger, then in fact they would all want to go to the same place, and it would be a giant city of people, and it would be a chaos, and So inherent in this is that right. Everybody can only base their decision making on what's going on locally. Now we can still, when we say, if I say these agents all do what's best for themselves, it's of course already constrained by the fact they can only see locally. So it's not truly rational. I mean, rational in the economic sense means you do the globally best thing to do. These guys are doing what's locally best. So in essence, these guys are boundedly rational because they have limited information, not because they're really computationally constrained, I suppose. They're doing a very simple calculation. Does that answer the question more or less? Okay.
Good morning, sir. So taking into consideration the bounded rationality and what Simon said back in 1957 in his paper, people faced real computational constraints. So I'm a person who actually works on contagion. So let's talk about information contagion. And suppose that if a person actually gets information, let's say, yes, recently NVIDIA, they launched Isaac Root M1, a humanoid robot, and that's just an information, plain information. And we have people in the economy or let's say in any other place, they have some sort of computational constraints. They can interpret this information to some certain extent. Let's say somewhere people are in such a way that they interpret this data, like this information in such a way that they think that in the future where we might actually have some robots from this movie called Terminator, like that. So my question is that people have different levels of computational constraints, and then they have their own levels of bounded rationality. Is it possible to model that in agent-based modeling?
Yeah, in fact, I would say not only is it possible to do it, I think it may be that there's no other way to do it, in the sense that it will be very unclear how to do that with mathematics, say, or very unclear how you would do that with game theory. So I think because because you can make your agent do whatever you want it to do, you could have it do precisely the way you described the process. You could have agents who have heterogeneous ability to understand the new information and then heterogeneous exposure to it. And you could, now, how they actually do it, of course, is an empirical question, right? How it actually play out. But yes, I mean, I think that maybe I should say the answer to that slightly differently and say, back to something I said earlier concerning, you really can, with agent-based modeling, you really can turn on all this stuff at once. So, I mean, you really can build very, very complex models with everything going on over here. There's nothing to stop you from doing that. And so I have had people say to me the following. People said, look, if you're going to have the ability to build agents who can do anything, Terminator agents or whatever it is, right? This modeling approach really is a modeling approach that you could use to model the economy on Venus, or you could model the social world of the Terminators or whatever. You can model for a zombie world. And the answer is yes, you can do that. If you want to build a model that's relevant to your research question or to your boss's supply chain problem or whatever, you will discipline your model with data. And so for that specific case you mentioned, unclear how much data we have on it. But for example, I think that if people want to measure things like what is the risk of AI going forward, AI doing different things, is humanity at risk? I mean, those are exactly the kinds of things you can do with this modeling approach. I mean, it's not one. Maybe back to the COVID question, we had no data in March of 2020 about how bad a pathogen COVID was. We don't really have any data today about what are the risks to humanity of modern AI. But as we get more data of this type, we can start incorporating that into our models.
I just wanted to know about the kind of emergent phenomena that may arise through these agent-based models, as each of them are bounded rationally. Like, do they exchange information between groups? So, for example, if it's something like migration, like one person goes to the other place, urban agglomeration or something, he goes back and passes on information to his neighborhood, and they all migrate to that place. So, if you have to model something like that, where agents are in conversations with each other, sort of a network in that sense. Do they form these collectives? Do these agents form these collectives in that sense? Connected in emergent.
Yep. Okay. So the question concerns kind of what are the dynamics of group formation and how does information flow in the groups and between groups? Bobby, just as a footnote, let me mention that many times in I mentioned a little bit about in the conventional modeling approaches, we typically have a microscopic level, microeconomics, a macroscopic level, macroeconomics. A lot of the stuff in between those two levels, like firms, regulators, regional tax laws, whatever it is, those things are not represented very well. Just the general process of group formation is not represented very well in conventional modeling approaches. Where are the coalitions or the mesoscopic structures in conventional theory? So an important research question, I think, is that we can at least address with agent-based modeling is, right, how do groups form? Are groups temporary or stable? Are they short-lived or long-lived? Are they formal or informal? And so we can start to model that kind of stuff within this modeling approach. For example, when it comes to migration, there have been a number of migration models built that I'm aware of in the last, say, 3 or 4 or 5 years, in which you have these kinds of chains of information flow, somebody is able to do a successful migration, and that gets back to his or her family or friends, and other people will take this information and make their own decisions with it. So yes, it's possible to do that, and I just think that's a general case of, or that's a specific case of the much more general point, which is going to be that we don't really have good models today of how groups, organizations, institutions form. We have highly idealized models of that, but my sense is that much of the best work with agent-based modeling in the next coming years, 10, 20, 50 years, will be on these kinds of things. That is, how do multi-agent institutions arise spontaneously and then evolve? And how does information flow between them, et cetera? So anyways, there's a huge variety of questions here associated with a huge variety of research problems to do, associated with, as soon as you relax these very strong assumptions that we all learn in graduate level economics, say, then a whole new world opens up with lots of rich things to work on. And my feeling is, without trying to overstate it too much, but there are Nobel Prizes laying on the floor here if you just pick up, if you can do build the right model, get the right answer. There's lots of good stuff to do. I mean, I gave a short talk last night to some students, and I mentioned that one of the very hardest problems, I think, in all of science is trying to figure out what are the things you should work on next. What are the kinds of problems that are going to have, that you can get answers to, that are going to be important answers. It's hard to know that before you do the research. And many things you undertake are going to produce either trivial answers or are going to end up being too hard to get good answers. So what are the problems that are going to give good answers? I think this is exactly the kind of thing that there's going to be, that we can do that today. Nobody really knows how to do it. I mean, people like Eleanor Ostrom worked on things like, how does a group of people, imagine all of us in this room, the 50 of us in this room, all using the same water supply. We know the water supply is finite. We all have our own wells. How can we write down rules that all of us should follow so we don't overexploit the water and end up all worse off? How can those mesoscopic structures between the purely microscopic individual person level and the highest government level, how can those intermediate structures grow, arise, remain stable over 1,000 years, as in the case of the Japanese wood gatherers? How can they be responsive to things like climate change? This modeling approach is set up to do that kind of work, but I think it's the case that we don't really know how to do it yet because we haven't built enough of these models.
I think we have time for one.
Does every agent-based model depend on past data, or can we model? Is there some agent-based model which don't depend on past data? Say, for example, we take something like stock markets, and we're modeling beta spreads or volume. Do we really need to use past data or current data to the Markovian database?
Yeah. So there are certainly examples of models that try not to rely too much on past data. I mean, the COVID models that were mentioned, or in the Neil Ferguson model that came out in mid-March of 2020, that had just some wild guesses about what the SARS-CoV-2 parameters were, and then it just, it tried not to use past data because it tried to say, what should we do going forward to stop the COVID from happening. So I guess the short answer to your question is yes, we can build models that don't rely on past data, but it's also the case then that those models end up being more speculative because they're not, in some sense, empirically grounded. I mean, think about, all of us have done some amount of natural science in our past. Right? You've taken the chemistry course or the physics course or whatever. And the reason why you believe the physics models is because they've been empirically verified, right? You believe the fact that molecules bond in this way that's described in the textbook because somebody has done the hard work to verify those things. When you propose a new agent-based model of something, if you don't have any data that is based on, it's going to be somewhat speculative and people may not believe it. I guess that's the risk, right? So every model involves some amount of data. I guess if nothing else, when you build the model, you have a mental model in your head for how the thing works, right? You've been working at this company for 5 years. You've seen how the supply chain gets disrupted. You have an intuitive model for how the supply chain works. When you sit down and finally start building the model, you're going to draw on that knowledge, even if you don't know exactly those details. So, I mean, I guess that's probably not a totally satisfactory answer, but I guess, for example, let's say we wanted to build a model for how the QWERTY keyboard came into existence. In that case, which we know it depends on the path, you'd probably want to build a model of the first typewriter users or builders, and you'd have to have something about how often the keys jam, right? You have to have some data about that anyway. So I guess, so yes, it is possible to build models that don't rely much on the past data, but I guess I'm just reacting a little bit that when we first started out building agent-based models, we had no data. And so all of the early models were data free, and only in the last decade or two have we really been able to build highly empirical models. So my particular bias, I think, is that we want to have more data in models, not less. But maybe one thing I have not mentioned is using agent-based models for pure theory. And that's something which is very doable. Right? If I can't, I say, let's build a theoretical model for how Bitcoin may become like a tulip bubble bursting, and if the price falls to zero. So I'm going to build a conventional model, put in a couple things over here. I don't really know how that's never happened before. Bitcoin has not gone to zero value. Could. No idea how that would work. But we build a model with blockchain and a bunch of other stuff going in there, and we'd say, if a bunch of certain kinds of users of Bitcoin just quit using it, maybe I don't know. But so I guess I'm just saying that if you say, I can imagine in my head a completely novel thing we've never observed before, can I build a model of it? And the answer is you should try. If you can get the thing coming out that you that you think could happen, then that's a contribution probably. Somebody can rightly say, though, they say, well, the mechanism by which you're producing this novel phenomenon, we have no data to ever say that could happen. They'd be correct. But you could still say, well, this is my belief how it might play out, right? A tsunami might hit, and we might all get drenched, right? It's possible. So I think it's a great question. Using the models for pure theory is possible. Right? If theorists tend to work on things they can solve mathematically, but there's no reason why this kind of tool can't be used. And early on, say we did try to do things theoretically when we didn't have much data. It's a great question, right? I think it blends in some of the previous questions about things like technologies are exactly the kind of area where we don't have much data about how it's going to manifest itself, et cetera. So you have to make decisions without, and I guess now one important idea though is what is the counterfactual, in the sense that you've got the model that's running, you may not believe the model, it's got a bunch of assumptions, but is the counterfactual just your own mental model, or is the counterfactual maybe that there's somebody from that industry, somebody who's an advocate for the new technology has quite a rosy forecast for how it's going to play out, which is their own mental model, but their model may not be based on anything concrete. It's just, once again, their hope that it will happen, right? So I think, but this is a great example where maybe that there are not very many models that are going to be useful simply because there's not much data. And so what you hope to get right, once again, it's a little bit like back to the hurricane or the monsoon forecast, is that if you have the correct mechanisms in place, you hope then that by putting in the parameters for this specific technology, that whatever the adoption mechanism is or whatever, you hope that that's all going to be the same, or that's going to follow some particular typical trajectory. I mean, I guess it's always possible to build bad models is the problem, right? And ex post, every model seems it got something wrong. I mean, these days we know that in all the COVID cases, almost all models got something kind of off a little bit. Yeah, yeah. And so maybe it's the kind of thing where only the time you built your 5th or 6th technology adoption model do you recognize that the first 4 you built were really kind of not that satisfactory, right?
And particularly difficult. So that's the kind of contradiction that I'm sort of facing. That particularly AI, which is very new, where the mechanisms we don't have the mechanisms yet in place, and this is the only solution that we have that we really simulate.
Yeah.
And when we get not so valid results, then it's like too much at stake.
There's a lot at stake, certainly, yeah. And so for some of these questions, it may be that no formal model is really ever going to be satisfactory, and you have to rely on just judgment and things. But I oftentimes think too, it's a little bit that just going through the process of trying to build a model forces you to specify what your own mental model is, and it may show you that you have some holes, as it were. Maybe you haven't thought through everything in your mental model, and that by trying to build a model, this is the philosophy where it may not be that when you build a model, it may not be that the final model is the real goal or the real value. The real value is you've actually gone through the process of thinking through what is the mechanism, what are the critical pieces, what are not. And maybe another way to say it too is that once you got some model built and you say, I'm getting some result that it seems like this is going to be okay, then you say, there's something, if I change it a little bit in the model, I get a different result altogether. It just shows you what are the sensitive points, right? Which things are, all this other stuff doesn't matter, but this one thing matters a lot. I got to really focus on this, because if I don't focus on this thing, it's all going to go in the garbage can or something, right? So I think that this is maybe this is more just a generic question of modeling as opposed to agent-based modeling.